Well, hello everybody. My name is Paul Abernathy, and welcome to another episode of Master the NEC, where we talk about the National Electrical Code. Now, this is an introduction into transformers. This is the very first video in the series. Now, we're going to break this down to make it as easy as possible, so there's going to be multiple parts to this series where we cover all the different aspects of transformers. We're going to talk about secondary conductors, we're going to talk about sizing, we're going to talk about primary conductors, primary overcurrent protection, secondary overcurrent protection, how it correlates to, for example, protecting of the panel board as well. If they have the secondary overcurrent protection, it's in a panel board on the secondary side of a transformer. A lot of information, a lot of topics can get confusing for people. We're going to talk about all those aspects, but on today's episode, it's an introduction. So in this introduction, we're going to talk about how to determine the primary transformer rated current and the secondary transformer rated current, because you need to understand what that current is, and that is the output of what this transformer can provide. Okay, this is and we're going to do it and give you what the maximum potential for this transformer is. Now, do you always have to use a transformer at its maximum potential? Absolutely not. Okay, many people do oversized transformers. Okay, it happens quite frequently. But if I'm getting all the bang for my buck, I'm going to make sure that I size it based so that I can get all the potential usage out of that transformer as possible. Now, remember, engineers size transformers based on what the load is. Okay, and that would be the load off the secondary. And so if it's, example, a Y transformer, then they're going to actually have to balance the transformer out with whatever loads they have. They're going to do load calculations, and that's going to pretty much dictate what the panel needs to be as on the secondary side, whatever's being fed from that transformer. And it also helps dictate the size of the transformer. Because a couple of things you have to remember. Transformers, three-phase transformers, which are delta or Y, and a delta being the Greek symbol for triangle is delta. And the Y is also a Greek symbol, and it is literally the formation of the transformer looks like a Y. Now, what's the difference? Well, the delta transformer looks like a triangle, and you have common connections from A to B, B to C, and A to C. Okay, so you have a winding between A to B, there's a winding between B to C, and there's a winding between A to C. Now, typically when we use a delta and we're trying to derive something like a 120, 240 off of a delta layout type of transformer, then we're going to center tap between the A and the C, and that's what's going to give us our 120 to grounded conductor. Okay, so this is kind of the layout, and we'll cover that when we get to that series, so I don't want to make it confusing. But in a Y-type transformer, it's very common at the center point. So phase A, phase B, and phase C are commonly tied at a center point. Okay, so that's why it looks like a Y. All right, so we're going to cover that today. We're going to show you, but one of the most important things at the introduction is to understand some formulas. And we're going to look at a graphic here in a minute, and it's going to be very overwhelming to you. But right now, all we're going to focus on this introduction video is dealing with how to calculate the primary rated current of that transformer and the secondary rated current of that transformer. So it's going to be a very light video. We're going to get you started into it. We're going to talk about some concepts as we go. Now, before we even do that, let's talk about transformers. What type of transformers are out there? Well, you have oil-filled transformers, and then you have what's called a dry type transformer. The difference, oil-filled literally has some type of oil or coolant material in there that actually encapsulates around the windings inside of the transformer, and that draws heat away from the core and the windings, which makes that transformer very efficient. And so it usually has a non-toxic, today's transformers anyway, I have a non-toxic type of oil inside of it that's going to help facilitate that cooling effects. It radiates it out and kind of dissipates the heat. It keeps it very efficient. It helps it last a long time. Whereas in a dry type transformer, you're only going to have air circulation. There's vent openings in it. Now, when you get into some of the larger type of transformers, then, of course, when you get into those, you might have something like air assisted, where you have some fans in there that's going to help blow the air across this core. And that helps keep it cool. And it allows for it to have a greater potential capacity to get you to whatever that maximum output is of that transformer. Because heat is not a good thing. Okay, if you have a transformer that's putting off a lot of heat, then it is very inefficient, and there's a lot of losses in there. And of course, we want to minimize the losses. Now, transformers are immensely efficient. Anywhere between 97, 98, and even 99% efficient, depending on the transformer, how it's constructed. So keep that in mind, that you have the different two types of transformer. Now, in all of our examples, we're going to focus on a dry type transformer because it's much easier to apply the rules. Although in our today, for example, primary current, secondary current, it's not going to be any different. It's just simply the function of the transformer is the difference. So we're going to focus on trying to talk about what the primary current and what the secondary current is. So let's go on and look at our presentation. So here's what we've got. So what we're dealing with today is this formula. And we have a transformer. Now we established, let's say this is a 75 kVA transformer. So as always, you want to make sure that you write those things down. So you write down that we're dealing with a 75 kVA transformer. Now, the primary side of this transformer, and you notice this is the delta symbol, and you see the Y. So this is a Y on this side, and it is a delta on this side here, feeding this side here. This is the delta side, and this comes down, and the output here is going to be the Y. Okay? So what we want to do is we want to find out the primary current rating of this transformer and the secondary current rating of the transformer. So it's pretty simple to do. First things first, this is the formula right here. You need to get used to this formula. So it's kVA times 1,000 divided by E times 1.732. All right? So let's come back to me and kind of discuss that a little bit. What is E? E is the voltage. What is 1.732? That's the square root of 3. We're dealing with a three-phase transformer, so we're going to need to use the square root of 3. Now, if this was a single-phase transformer, then we would need the 1.732, okay? But in this case, it is three-phase in our example. So we want to kind of stick with this example in order to calculate it out because it's simply the same way if it was a single-phase. You just simply skip the 1.732, okay? So it's really just that simple. So in our application, we had a 480-volt primary line voltage. Okay, so if you go back to the graphic and we look at the presentation, we can see that what we're going to do is we're going to take the 75 kVA times 1,000. That's going to give us 75,000 VA. So over here you see I've kind of simplified it. And then since it's E is dealing with the voltage, it is 480 volts as we see here. And this is going to be typically on the nameplate of the transformer, or you're going to know that when you purchase the transformer, you know what you're looking for. Because you need to know what your output's going to be. So in this case right here, it would be 480 volts times 1.732. Okay. Now, if you come back to me, we'll go on and calculate that out. So we got our trusty calculator out. So we're going to actually do it. I always like to work these things out with you. So it's 480 times 1.732, and that equals 831.36, okay? So that is actually what. Now, for us, we can actually use the 831, okay? We can drop off the 0.36, so we can use the 831. All right, so if you go back, you'll see that I actually give you some shortcuts for that in the presentation, some things to keep to memory. So anytime you're dealing with 480 volts, just remember 831. That's all you have to remember. So it would be whatever the kVA is times 1,000, because we need to convert it to VA, and we divide that by 831. And that's just a shortcut to get you it. Now, if we're doing the secondary, the same math, everything still applies. You take the same kVA. The kVA doesn't change from the primary to secondary. That does not change. So you take the 75,000 that we'd already done, and you divide that by 208 times the square root of 3, or if you remember 360, that's your shortcut. Now again, if we use our calculator, and I'll just keep it on the presentation, you can just do it yourself. But if I take the 208 times 1.732, that gives me 360.256. Well, I can just use the 360, and that will be fine. Okay? And we're going to calculate that out all in a minute. But there's one more that I don't show on the screen. In case you're dealing with something that might be 240, then there's a shortcut for that as well. So you simply take the 240 and you do that times 1.732, and we're going to do it here in our just to give it to you. So 240 times 1.732, and that is 415. So that is another shortcut in order for you to just skip that math, especially if you're taking an exam. I mean, the time is of the essence. If you can get done with the exam and save yourself some time, that way you get more time to check over your questions and things like that, then it's a benefit to you, right? So just remember, if it's 480 and you're doing with the transformer calculation, remember 831 is the bottom equation in that division. If you need to deal with a 208, remember it's 360. If it's a 240, then remember that it's a 415, and that's what you're going to divide into, okay? Pretty simple things to remember, but if you're taking an exam, that can be beneficial to you, because on an exam, you need to know in many cases how to calculate the primary current rating of that transformer or the secondary current rating of that transformer, because everything else builds off of that. The overcurrent protection for the primary winding or the overcurrent protection from the secondary winding, all of that is really based on that current, that transformer's primary or secondary current rating. And you have to be able to do that calculation. So it's important to remember how you do that if you have an exam and it asks you a question about the overcurrent device for the primary or secondary protection. Okay, it's important to do that. Also, it's important if you're sizing the conductors on the primary and secondary side. So, and we'll cover that in another video where we go into detail about those things. We really want to talk about the basics here of how to determine the primary and secondary current ratings, and that's all we're talking about now. So let's go on and get back to the presentation. All right, so here we are at the presentation, and so we're going to finish this thing out. And so let's go on and do the math, if you will. All right, so in our case, it was 75,000 and divided by, so 75,000, go on and work that out, and I'll come back to me. That way it's easier for you to work it with me. So we'll take your trusty calculator, and we'll do 75,000. And we're going to do that divided by 831, and that is 90.25 amperes. So for all intents and purposes for our calculation, we'll take the 90 amperes. So the primary rated current of this transformer, this 75 kVA transformer, is 90 amperes. And everything else is going to build off of that. So this is our starting point. All right, now what about the secondary? It's just as simple. So we take the 75,000 and we're going to divide it by 360. And that's going to give us a 208.33. Now we can drop the 0.33 and we really only need to deal with the 208 amps. So that is our secondary transformer rated current. Okay, so that's pretty much how you size the transformer's capacity. Okay, the primary current rating. Okay, and so it's really that simple. So if you're taking an exam and you need to know what the overcurrent protection device is under 450.3 for the transformer's primary or the secondary, you have to start out with this basics. Okay, you have to be able to know how to take it and take the kVA, convert it into VA, and to divide it over the voltage times the square root of 3. But we give you these shortcuts. If it's 480, use 831. If it's 208, use 360. If it's 240, then you use 415. And that goes on the bottom portion of your division. So you've got the top is your VA, and the bottom is your actual shortcut that we did. Okay? So it's really that simple to get you the basics. And of course, we're going to get into the more in this series where we kind of go into all of the aspects. But what I wanted to do is give you the tools to build upon. And these are your tools. Now, if you want to learn about the basics of how transformers work, then we'll have a video for that. If you want to know how to size the secondary conductors, we're going to have a video for that in this series. If you want to know how to size the primary, a video for that. How about the grounding and bonding of a transformer? All of the aspects of the supply side bonding jumper, the system bonding jumper, the equipment grounding conductor on the primary side, we'll have a separate video all for that so that you don't have to take it all in one big lump. You can learn it as you go, watch the video that you need to help build your skills and help make you a much better electrician. Thanks again for watching. Stay tuned for the next episode.